Welcome to this explainer. Today, we're diving into a genuinely fascinating presentation that attempts to do the impossible, merging two completely different realms of theoretical physics. I mean, if you've ever found yourself wondering how the macroscopic, heavy world of gravity actually connects with the microscopic, weird rules of quantum mechanics, you are absolutely in the right place. We're looking at a framework that tackles this head-on by looking at the very geometry of space-time itself. Now, fair warning, it is dense and it's highly technical, but if we break it down step by step, the underlying logic is just beautifully clear.
So let's jump right into the core question driving all of this. How much does general relativity actually know about quantum information? Because this is the centerpiece of the whole puzzle. Somehow, the classic rules of gravity, just mass existing in curving space, are intimately aware of quantum entanglement happening on the edges of that space. It turns out that even semi-classical gravity in the bulk of space inherently knows a massive amount about quantum information on the boundary.
To navigate this highly technical landscape, we've got a clear roadmap. First up, gravity meets quantum information. Second, the connected wedge theorem. Third, focusing the light sheets. And finally, Bousso's entanglement wedges.
Starting off with Section 1, gravity meets quantum information. We need to set the stage here and understand exactly why physicists are so driven to merge these two distinct frameworks in the first place.
It really comes down to finding a language that translates physical scattering in space into the language of quantum entanglement. Think of these as two separate islands we're desperately trying to connect. On one side, you have the bulk. This is the geometrical space where gravity operates, totally governed by general relativity. And on the other side, we have the boundary. That's the outer edge of this space, where quantum information and entanglement completely rule. The holy grail of this research is figuring out how an event happening deep inside that bulk translates to the quantum rules out on the boundary.
But here's the catch. Trying to understand flat holography directly is incredibly difficult. Actually, it's pretty much a running joke in the field that it might not even exist. As the speaker points out, subtle is probably the polite word for it. And that is exactly why researchers are looking for a backdoor approach. They desperately need a framework that lets them play with these concepts without getting totally bogged down by the sheer impossibility of standard flat holography.
So what's the workaround? Well, the crucial point is that by studying how particles scatter in a highly controlled 3D space, like an anti-de Sitter or ADS space, physicists can take those flat limits and successfully import them into flat space models. Instead of tackling the hardest problem on day one, they put probes on the boundary, let them meet in a tiny little region in the bulk, and study that exact scattering process. Because ADS space acts almost like a box, it naturally contains the physics, and that makes the math of these scattering configurations dramatically easier to manipulate.
Which brings us to Section 2, the connected wedge theorem. Now that we know why we're doing this, let's introduce the actual bridge itself, developed by physicist Alex May. This theorem is literally the linchpin of the entire framework. The connected wedge theorem states that if you have scattering happening in the bulk, you are mathematically guaranteed to have a certain amount of boundary entanglement. Specifically, it bounds the mutual information by an order of 1/4g. This is huge because it provides a direct, concrete mathematical link between a physical event in gravity and a quantum measurement of entanglement.
Let's distill that into a more colloquial, everyday takeaway. If things are bouncing off each other deep in the bulk, the quantum entanglement regions on the edge absolutely must be physically connected to one another. There's no way around it. Interestingly, this whole approach was inspired by quantum tagging results, basically the idea that you need a certain entanglement resource to even spoof a local scattering process.
And this whole concept relies on what we call a 2-to-2 scattering process. What does that mean? It just means two signals are sent in from the causal past, they meet up and scatter in the bulk, and then two signals are sent out to the causal future. If that 2-to-2 process happens entirely within the bulk and not out on the boundary, then the boundary regions representing those inputs and outputs are inextricably linked.
All right, moving right along to Section 3, focusing the light sheets. Let's see how this bridge is actually built using the wild geometry of focusing light sheets.
This is where the geometric proof of the theorem really comes to life. The speaker brings this delightfully informal passion to some very dense math, unapologetically relying on the Raychaudhuri equation. They essentially shoot focusing light sheets anywhere they want, simply because, well, they, quote, enjoy the flexibility it gives them. But make no mistake, behind that playful flexibility is a rigorously tight mathematical proof.
The secret weapon here is indeed the Raychaudhuri equation, because the expansion of a light sheet, or a null congruence, is negative or zero. Shooting these light sheets outward creates surfaces with lower and lower areas. You're basically following light sheets up and back down again, which systematically forces the geometric area to decrease as you move along.
So, physicists can make this work by following 3 strict geometric steps. They literally trace the topology of light sheets outward from the scattering region. Think of it like nested Matryoshka dolls. The light sheets travel outward, they meet up to form a sort of ridge, and because Raychaudhuri's equation ensures the area is always decreasing, physicists can mathematically prove that the area of this ridge bounds the mutual information on the boundary.
And here is the grand finale of that proof. Through pure geometric focusing, they have perfectly translated a physical bulk space area directly into a quantum information measurement. The area of that geometric ridge fundamentally dictates the minimum amount of mutual information that must exist on the quantum boundary. It is an absolutely stunning connection.
Finally, we reach section 4, Bousso's entanglement wedges. Now we're going to zoom out a bit to see how this connects to the broader universe of holography, specifically the work of physicist Raphael Bousso.
See, once we have these bounds, we can apply them to bigger questions about how holograms actually function. Bousso realized that when you're dealing with complex mixed states rather than simple pure states, we actually need 2 distinct definitions for entanglement wedges, a maximum and a minimum. In a pure state, these might be the exact same thing, but in semiclassical bulk geometry, you need E max to define the absolute largest reconstructible region, and E min to define the absolute boundary of what you simply cannot access.
To make these wedges mathematically rigorous, Bousso set up 3 highly specific geometric rules to define that max wedge. First, it has to be inside a fundamental complement. Second, it must be anti-normal, meaning the expansions at the corners have fixed signs. And third, there has to exist a Cauchy slice extremizing generalized entropy. By setting these strict geometric rules, he lets the math do the heavy lifting. And since the scattering setups we talked about earlier naturally have controlled signs at their corners, they plug perfectly into Bousso's complex definitions.
But here's the thing. Proving these geometric connections and establishing these bounds is truly just step 1. Yes, it's a tremendous leap in connecting the bulk to the boundary, but it leaves us staring down a profound question. What deeper secrets of flat space holography is this geometry waiting to unlock? Just how much more of our quantum universe can the simple shape of space-time reveal? It's an incredibly thrilling frontier, and I hope this explainer helped illuminate the path forward for you.